Hi, my name is Aishi, and welcome to part 2 of our lecture on the fluid mosaic model. Let's begin with a discussion of the fluidity of membranes. Sometimes people think that membranes are these static things that don't move around very much, but in reality, both phospholipids and proteins will do quite a bit of moving. As you can see here, phospholipids can have a lateral movement where they just sort of swap positions with their buddies, as shown here. And it's sort of like a person moving through a crowd. It's decently easy to do. And this will happen quite often, as you can see. It's an average phospholipid will swap places with a buddy 10 million times per second. And what this translates to is that a phospholipid can travel about 2 micrometers in 1 second. And that's a pretty crazy distance. What's a more rare form of movement is the vertical displacement, or it is also called a flip-flop. And this happens about once a month. And the reason for this is because in order for these two phospholipids to swap places, the head has to go through this hydrophobic region. And since the head is hydrophilic, it really doesn't want to do that. And that's why this is a rare occurrence. Now, proteins, they also move. And there's actually a very clever experiment that they did to show this. What they did was they had a mouse cell and a human cell. And they fused these cells together, forming a hybrid cell. And they paid close attention to where the mouse proteins were and the human proteins were. And what they saw was that after an hour, the mouse and human proteins were all mixed together and interdispersed within this single hybrid cell. So proteins also move. Another key factor that determines the fluidity of membranes is the degree of saturation of hydrocarbon tails. Now, I've drawn a phospholipid here with 2 fully saturated hydrocarbon tails, and as you can see, they're perfectly straight. And here I've drawn a phospholipid with 1 saturated hydrocarbon tail and 1 unsaturated hydrocarbon tail. And the unsaturated one, you can see that there's a kink in the tail. And the reason behind the kink is because there's a double bond between the 2 carbons. And so what you have is you'll have this weird shape that occurs within the tail. And in this molecule, in this hydrocarbon tail, I've only drawn 1 kink, and so there's only 1 double bond. But there are other cases where you can have multiple double bonds within the hydrocarbon tail, and you'll see multiple kinks. And I've sort of drawn these little diagrams below these phospholipids, showing how tightly the membrane can be packed full of phospholipids. As you can see here, with fully saturated hydrocarbon tails, the phospholipids can be packed very closely together. They're sort of, side by side, all of these little phospholipids sticking together. And they're able to get so close because their tails are straight. But when you start having unsaturated hydrocarbon tails, well, they stick out. The kinks exist, and these the kinks within the tails make it much more difficult to pack these phospholipids together. And so you have a more fluid membrane in this case compared to the saturated case. Now, animal cells have yet another way of regulating membrane fluidity. Animal cells will actually use cholesterol within the plasma membrane to either help increase membrane fluidity or decrease membrane fluidity. Cholesterol acts as a buffer. So if you have high temperatures, then what cholesterol will do is it'll reduce the membrane fluidity by preventing these phospholipids from moving around too much, because you have these little cholesterol molecules in the way. But let's say the temperature is really low. Well, the cholesterol molecules will prevent these phospholipids from coming too close together. So when the temperature is too low, cholesterol will increase membrane fluidity. So cholesterol acts as a buffer. It tries to maintain the optimal level of fluidity, and it acts opposing the temperature effects.